Assalamualaikum warahmatullahi wabarakatuh. My name is Nakib Fahmi, 22006710. For my part, I will explaining about the stability of an RLC filter circuit. So this is how the circuit diagram of our second order system, the RLC filter circuit, and the equation below shows the transfer function of the circuit, which is given as 1 over S square LC plus I plus SRC plus 1. So before we jump to the stability, there is 4 cases of the system response will be highlighted in this video. The system response is basically depending on the damping ratio value. So for this system, the damping ratio formula is given as R over 2 times with square root of C over L. Whereas for the stability of the system, we can determine by looking at the pole position on the plane of the pole zero map. Let's take a look for the example here. So by using the damping ratio formula, when R equals to 0 ohms, the damping ratio is 0. So the response is stated as undamped, while the pole position is on the GW axis. So the system is stated as marginally stable. Next, when R equals to 10 ohms, the damping ratio is equals to 0.2086. Since the value of the damping ratio is between 0 and 1, the response is stated as underdamped, while the pole position is located on the left half plane, so the system is stated as stable system. So for the next example, when R equals to 48 ohms, the damping ratio is 1.0013, which is approximately equals to 1. So the response is stated as critically damped, while the pole position is located in the left half plane. So the system also stated as stable system. Next, when R equals to 1000 ohms, the damping ratio is 2.0861, which is the value of the damping ratio is more than 1. So the response is stated as overdamped, while the pole position is located in the left half plane. So the system also stated as stable system. So this is how the results of our second order system response for the undamped, underdamped, critically damped, and also overdamped.
Next, we're going to discuss on the system response of our RLC filter circuit. So in this discussion, while changing the value of resistance and the system itself, either to be a open loop, closed loop, or closed loop with a PID controller, we're going to check its rise time and its settling time. So what is rise time? Rise time is the time taken for the value from 10% to reach 90% of its steady state value. So this time we want to be as small as possible, as we can reach its stable state much faster and not oscillating around the value, making it unstable. Next is the settling time, which we also want to reduce, as less settling time meaning we can reach the correct value faster. So for our graph, I will set the color green to be the input open loop system, blue color is the closed loop system with the PID, and finally the red color is a closed loop system without PID controller. First, we'll take a look on the underdamped system response, which correlates to R equals to 0 ohms. So in this response, the input given is a step input with a gain of 1, and we can see that the output for a open loop system the PID controller and the closed loop system are sine waves, which means that it keeps on oscillating. We can conclude here that there's no rise time or settling time, since the wave does not settle at any value and it keeps changing, making the system unstable. Next, we will look at the undamped system response. Similarly, we will give a step input with gain of 1, and we will see the output. All three different systems, the open loop system, the PID controller system, and the closed loop system, have the same rise time. But after the rise time, they have an overshoot, which will then oscillate until they get a stable value. For the open loop and closed loop system, both settling time and rise time are the same. However, we can see that in the closed loop system, the gain actually is half of what it used to be, while the PID controller keeps on oscillating until it get to the value that is desired, which is 1. So we can say that the settling time for the PID controller is larger. Next, we will check the critically damped system response, in which when the R value reaches 48 ohms. So similar like before, we'll give the step input and we'll check each system's response. So for the open loop system, the rise time is very quick and settling time is almost zero, as no values oscillate around 2% of the gain 1. This also happened in the closed loop, which is the red line, but similar like before, the output will be half of what is intended. Now, the PID controller keeps on oscillating until it gets the gain that it want, which is 1. So we can say that the rise time of all these three closed loop system, open loop, and PID control system is the same, but the settling time for PID is much higher, while the settling time for open loop and closed loop is almost zero. Finally, we will go through the overdamped system response, in which the value of R is very high. In this example, we will use R equals to 100. So similarly, we will give a step response with a gain of 1. And the difference between an overdamped and a critically damped system is the rise time. So for an overdamped system response, we can see that the rise time is much larger and the settling time is existent in this. It's not zero like before. So an open loop will directly get the gain 1, while the closed loop will get a gain of half. And similar like before, PID, after rising until 90%, it will keep on rising until it get the value that is intended, which is 1. So the rise time for open loop and closed loop is similar, while the rise time for the PID is much larger.
Hi, my name is Tan Junyan, and I will be presenting about PID controller of an RLC filter circuit. PID controller, also known as proportional integral derivative controller, is an automatic control system used to regulate different parameters like temperature, pressure, and speed. A PID calculates the error and the difference between the actual value and desired value, and then sets the deciding parameters accordingly. This error is continuously being calculated until the process stops. For the proportional term, adjustment is made in real time based on the current error, which helps in quickly correcting deviations. For example, if the circuit's output is too high or low, the proportional controller adjusts the input proportionally to reduce the difference. Next, integral terms is responsible to speed up the process towards acquiring desired values and eliminating the errors due to proportional term. However, as integral terms acquire the sum of past values to reduce the error, it could cause the system to overshoot from the desired values. Lastly, derivative control predicts the future error by observing how fast the error changes. and help to stabilize the circuit by dampening oscillations and reducing overshoots. When we combine proportional control, integral control, and derivative control into our PID controller, all the control terms can balance on another to bring stability, accuracy, and responsiveness. The graph above is the comparison of input response and the output after the PID controller.